Hello everyone, I'm Austin Erickson. I'll be giving this presentation today about the effects of depth error on visual target identification tasks in shared gaze augmented reality environments. I just wanted to start out by saying that both myself and my colleague Nahal Narozi contributed equally as primary authors to this project. Alright, so AR collaboration has been a hot topic in the field over the last couple of years. It can bring people together in a local environment, or it can bring remote people together in this virtual environment. But it relies heavily on verbal and nonverbal communication cues. However, whenever we put on a HMD, we kind of lose we reduce the number of these social cues, and we reduce the quality of them. Just by wearing the headset, it's hard to tell where someone is looking, and it's hard to tell their facial expression in general. So in order to regain some of these social cues, additional hardware and sensors are needed. So as we introduce eye trackers and depth sensors, we regain some of the information about where our collaborators are looking. For instance, with just the AR HMD alone, the only information we have is head orientation. So they're just the head direction of where they're looking, so we don't know exactly what they're looking at. However, once we add an eye tracker into the equation, we have a general direction of where they're looking, although we may not know which 3D point along that direction they are looking at. But once we add that depth sensor into the mix, we can finally kind of conclude the specific 3D point that our collaborators are looking at. The downside to adding these two layers of hardware is that they are prone to error, both network and accuracy errors. And these errors have big impacts on user performance. We ran a study on this in the past, and we showed that accuracy and latency errors specifically can have big impacts on user performance when they're relying on using this shared gaze information. Additionally, there are many different ways that this gaze visualization can be shown in augmented reality. So how does this visualization impact user performance? Can just changing the way it's shown impact the way that they perform in the task? So we designed two experiments, the first of which investigates the impacts of depth and horizontal accuracy errors in shared gaze collaborative environments, and then the second looks at the impact of the different visualization methods on user performance. So our study scenario consisted of a participant who would come in and wear the Microsoft HoloLens. On the HoloLens, they would observe a crowd of 8 people who are pacing perpendicular to the participant in the area in front of them. Next to the participant is a virtual partner who is sharing his gaze information with our participant. So our participant can see where this virtual partner is looking. During the task, the virtual partner will look at one of these 8 people in the crowd, and then our participant will be tasked with trying to figure out who it is that he's watching. What makes this difficult, though, is that the gaze visualization is based on depth information, so it collides with the first object along that virtual partner's gaze path. So if we look at the figure on the right side of the screen here, we see that our virtual partner is observing person D. However, when person C crosses in front of that path, it will temporarily look like the partner is watching C instead of D. Additionally, when persons A or B, who are closer, cross this path, it will temporarily look like the partner is looking at A or B as well, until they clear the path, then it resumes focus on person D. So it's kind of a difficult task. To simulate natural gaze behavior, there are 3 points of interest on each of the virtual humans in the crowd. The partner can be looking either at the person's head, at their chest, or at their waist, and has a random chance of switching between these 3 points every so often. Additionally, there's a unique number which floats above the head of each of the virtual humans in the crowd. This number is used for our participants to identify which target they believe that their partner is watching. So they'll call out that number out loud when they think they know who their partner is observing. Here's a quick screenshot of our study setup. So we have our partner wearing the HoloLens, our participant wearing the HoloLens on the right here, and she is viewing this crowd of virtual people. To her left stands this virtual partner who is shown as a police officer and is sharing his gaze information, which in this case is a gaze ray, truncated ray, which is observing the lady in the purple shirt. So this ray terminates on collision with this lady's face. However, we can see that this person in the gray shirt with the 1 above their head is about to walk through this line. When that happens, instead of that ray terminating on the lady that he is observing, it will temporarily terminate on this person in the gray shirt until he clears the path. So this first experiment consists of 4 independent variables, which will be explained in depth in the next couple slides. But just to name them, we have error type, so 2 different error types. There are seven different levels of error for each of those error types. There are 2 target depths in which a target person is chosen from in the crowd. And then there are 2 visualization modes in which that shared gaze information can be displayed to our participants. So starting out with our error types and error levels, we have depth-based errors and we have angular-based errors. Our depth-based errors have 7 different levels. At 0 degrees of error, or 0 error level, it will appear right on the depth of the target. So that first collision point with the target that our partner is observing. With positive amounts of depth error, that gaze visualization will stop short of reaching the target and will hover in space, leaving a gap between the visualization and the target's body. For negative amounts of depth offsets, the opposite occurs, and that the gaze visualization will pass further through the target than it is supposed to. So for instance, at -1 error depth, or 35 centimeters, that visualization will pass partially through the virtual human and may be partially occluded by their model. At further errors, like -2 and -3, that gaze visualization will terminate significantly further back behind the target. Similarly, for angular errors, these are on the horizontal axis instead of depth, but they still do have a depth component to them. At 0 degrees of error, that gaze visualization is going to fall right on the target and be centered. At plus or minus 1 degree of error, that gaze visualization will be rotated in 1 degree to the left or the right, but it will still fall on the target. It will just be off-centered. At -2 degrees or plus 2 degrees, it will be right on the edge of the target. And so depending on that target's motion and their animation and their movement in the scene, sometimes that gaze will hit the target and sometimes it will fall off, causing it to be projected further back into the scene. Finally, at -3 and +3 degrees of error, the gaze visualization consistently misses the target person and will consistently reach further back into the scene. For a third independent variable, we have the target depth. I mentioned before there's 8 people in our dynamic crowd, but there are only 2 positions at which our target person can be chosen. Those are either at a near position of 3.15 meters or a far position of 5.25 meters. The appearance of our virtual humans is shuffled every condition, so that people are randomly assigned a different order. However, out of this order, the only 2 positions for our targets are going to be these 2 positions as shown in the figure. For our fourth independent variable, we have 2 different visualization methods. So the first of which is called truncated ray. It is a line that starts from our virtual partner's head and extends from his head out towards the person that he is observing. Upon the first collision point along that ray, it will terminate. So usually it terminates right on the target. However, if something closer in the scene intersects it, it will temporarily terminate on that closer person. On the right side of the screen, we see our 3D cursor visualization. Instead of having that directional component, which is the ray, the 3D cursor is just a floating 3D object that will appear at that termination point. So in this case, it's shown on that lady in the purple shirt's head. Now, when we introduce the depth offsets, these visualizations will either extend further past this target, and for instance, be further back towards the guy in the vest, or will stop short of reaching the lady in the purple shirt and will be hovering in the air short of reaching them. This is our first page of results from the experiment 1. On our vertical axis, we have our accuracy rate, which would be 100% if our participants made no mistakes, but it is a difficult task, so there were some mistakes made. On the horizontal axis, we have our depth offset. So these are our depth accuracy based errors. On the far right bottom corner of the screen, you can see there's kind of a mock-up of our virtual partner and participant. As we go through these, I'm going to use these to illustrate the different levels and the different measures that we got on this graph here. So for instance, on this first slide, we're at plus 105 centimeters of offset. This is a visualization that falls short of reaching the target as shown at the bottom of the page, and it does have significant impacts on user performance. So they make a lot of errors in this offset. As the offset decreases and we get closer to the target, the errors are reduced. So they're actually performing better, but still not great. Once we reach an offset of positive 35, participants start to do pretty well, and they're close to 100% accurate. Same thing at 0 centimeters of offset. However, once we reach minus 35, certain visualizations are occluded by the target person. So for instance, the 3D cursor is hard to see when it's directly behind that person's back. So we see a spike in our accuracy rate for those particular visualizations at this offset. As we continue back, it's actually easier to see if it's further back behind the target than it is if it's immediately behind them. So we see an actual increase in performance here. And then finally, as we get further away from that, we see another decrease in user performance. Now we're going into our horizontal accuracy errors. So similar to the past slide, we have our vertical axis, which is our accuracy rate, which would be 100 if they're making no mistakes, and it decreases as they make them. On our horizontal axis, we have the degrees of rotation, which are applied to the gaze visualization. On the far right, we also have this mock-up, which kind of shows what our participants would see from this gaze visualization for each of these levels. So starting out, we're at positive 3 degrees of rotation, and we see a pretty sharp decrease in our user performance. As we get closer, the performance increases until we get to plus or minus 1, at which point we're at near 100% accuracy. At 0, we actually see another slight decrease in performance, which is interesting. And then at minus 2 degrees of rotation, we see another decrease in performance, followed by another decrease in performance at minus 3 degrees of rotation. So the main takeaway from this is that the angular error decreases user performance for levels that are higher than plus or minus 1 degree of rotation, and that these depth errors tend to decrease performance at or above 105 centimeters of depth offset, and also when they lie very close behind the target at that minus 35 centimeters of offset. So from our results, we did a lot of comparisons between that truncated ray visualization and our cursor visualization. And between our objective and our subjective measures, we found that the truncated ray offers better performance, significantly higher user confidence, significantly lower cognitive load, and significantly higher usability than the cursor visualization. So there's a lot of good benefits to this. And we believe that this is because it includes that directional component that the cursor lacks. So now we're going into experiment 2, which investigates several more visualization modes. So we have 2 variables for experiment 2. The important thing to note is that for this experiment, there's no error being applied to those gaze visualizations. They're always going to fall right on target. For this, we use that same 2 target depths in the crowd, and then this time we offer 2 new visualization modes. On the top left, you can see our truncated ray, which we used in the past experiment. Below that is the cursor, which we also used. In the bottom right corner, one of our new visualization modes combines the 2 of those. So it's truncated ray with a cursor at that termination point. Additionally, we use extended ray, which is a ray that does not use depth information. So this ray is projected through the target to a theoretical infinity, which we set to be 20 meters for a termination point for this experiment. This outlines our results for experiment 2. We did see a significant main effect of our visualization type on the response time of users as they were making their guesses in the task. What was interesting was that our participants were 100% accuracy when were 100% accurate when no error was applied. So we had 100% accuracy rate here. And it's also interesting that we did not see a significant effect of the depth of the target on their response time. So on the left here, we can see the graph of the response times broken down into the different visualization modes and the different distances at which the target could be displayed. And for this, we see that the ray and cursor offered the best performance when that target was up close. And actually, the truncated ray offered the best performance when the target was further away, although the difference between them was not significant. Our subjective results for this experiment also showed that users significantly preferred that ray and cursor visualization compared to all of the other visualization modes. So our main takeaways are that the users prefer and are more confident with that ray and cursor visualization than all other visualization modes. And we think that this is due to the combination of that directional component with the 3D cursor. So the cursor gives you a 3D focal point that you can use to judge depth, and then that ray gives you the direction that that partner is looking. Additionally, we found that users preferred the truncated ray significantly over the cursor visualization, which again goes back to that inclusion of that directional component. So our take-home messages from these 2 studies are that the visualization modes that combined both depth cues and directional cues offer the best user performance in shared gaze scenarios. Also, an interesting takeaway is that our depth errors were asymmetric, and that stopping short of the target offers worse performance than if you had passed too far through the target. So thank you guys so much for your attention. I will be around in the chat to answer any questions. Thank you.